Hello, so this video will be discussing DC sources. A source is a source of energy, okay, supplies energy to the unit, okay. This is like the faucet, if you want to use the water analogy. And then the load is whatever is consuming energy. It could be a resistor, it could be a lamp, a heater, anything that's converting energy from one form to another or consuming energy. So as I explained, a source is a supplier of energy, okay? And then usually, you can have two options, either a direct current or an AC current, but for the purpose of this presentation, we're talking about direct current, which is a flow of continuous current, okay? It doesn't change direction, only in one direction. An AC current is always changing direction, positive and negative, okay? Um, yes, it's caused by a voltage source with fixed polarity, okay? The polarity does not change. So to create a DC current, it requires converting one form of energy to the other. So it's either light, heat, magnetic energy, chemical, electrical energy to another type. Yes, you can get a DC current, an AC current, and convert it to DC current, or mechanical energy even. So through the presentation, we'll be talking about examples for each. So the first example is a thermocouple. A thermocouple is a thermal energy transformed into electrical. So we use two different metals together, okay? So here, for example, iron and copper, okay? They're mingled together, they're welded together, okay? And then by applying heat to that connection, electrical force is generated. Okay, it's not a significant electrical force to make a battery, but this electrical force, we use it to sense temperature. So here is an example for a thermocouple used inside a boiler. So here is the thermocouple right next to the pilot burner. Okay, if the thermocouple is sensing temperature, it lets the gas flow. If there is no heat, or the heat is not high enough, the thermocouple would stop the gas. So it's kind of like a safety feature. Okay. Thermopile is a group of thermocouples wired together to produce higher voltage response. So again, they're used in temperature sensors. So kind of like accumulating batteries, you get a higher voltage and more sensitive response. That's what a thermopile is. Mechanical to electrical is the piezoelectric effect. So the piezoelectric effect is when you apply mechanical force, okay, to a crystal, okay, whether it's pressure or twisting, this this crystal would start generating voltage, okay, and this is used in pressure sensors, in microphones to sense vibrations, and igniters for lighters and gas grills. So it's called the piezoelectric effect. Voltage is generated on the opposite sides of the crystal, as we've seen before, as a result of pressure or twisting, used in pressure sensors, crystals, microphones. The very known example is a solar cell. Converts light energy into electrical energy, and this is a booming field nowadays, getting much more efficient and less expensive. Back at the time, or still to today, a solar cell was used, or even today, you get cell phones batteries, cell phone recharging backup battery that's relying on solar panels. Okay, magnetic to electrical. So when you have a coil of wire and you pass a magnet through it, it would create a voltage. This is a phenomenon known in electricity. So what happens is we have a huge magnet, And then in here, we create a coil. So this is a coil of wire, and this is the magnet. And then when that coil turns inside the magnet, so there has to be something turning, so there's a mechanical effect here, okay, it creates electricity. And the very simple example is a bicycle light. So in a power generation plant, this force could be hydroelectric, like in a dam, could be pressurized steam, could be wind. This force spins the turbine. So here is the mechanical energy. Turning a shaft, and that shaft would turn the huge coil inside the generator, and that would create electrical energy. So electrical to electrical is the example I said. A classic power supply would take from here or from here AC, and then it would from here it would get you out DC current. That's electrical to electrical conversion. The chemical to electrical conversion is the basic battery we all use, called the voltaic cell. It has three basic components. The electrolyte in here, which could be liquid, or we call it paste, and we'll explain that later. You have two electrodes, a negative electrode and a positive electrode. And we talked about the electrolyte. So the electrolyte is a substance containing free ions that behaves as an electrically conductive medium, usually an acid. And if you guys recall, I explained that in class. If you have a beaker, and you have in that beaker acid, and let's say you get a piece of metal, let's say it's zinc. If you get that zinc inside the acid, what's going to happen? Let's say the acid is not so concentrated. The zinc will start melting. So the zinc metal here will dissolve, will react with the acid, and will change into zinc ions. Okay? And in that process, an electron is lost. This electron, if you have two electrodes, this reaction happens on one side, which is this side, releasing electron, and that electron would flow through the circuit and come back in here. So this is a simplified concept. It's kind of like the acid is eating through the electrode, freeing up electrons that go through the circuit. So we say it's usually two dissimilar metals. Electrolyte react, causing an excess of negative ions, which we talked about, an electron, and on the negative plate, an excess of positive ions on the positive plate. And that would create enough voltage for a lamp to operate, and it can keep going till you consume all the acid, basically. So here are the cell types. You can have a primary cell, which have a paste, dry electrolyte, which is a dry cell. This is not rechargeable. Once you use it, garbage. And it has carbon and zinc electrolytes. And the paste, these are different types, carbon, zinc, alkaline, manganese, and lithium types. The secondary cells is rechargeable, kind of like you can have, because it has a liquid electrolyte. So when the acid is gone, you can basically recharge it. You can add more acid and make it more functionable. And then, as it says, lead acid, nickel, cadmium, metal hybrid, and lithium ion. These are the different cell types. So here we're going to talk about battery capacity, which is like how much energy is stored in that battery. And it's usually set in amp hours. Okay, and I hope it rings a bell because remember we talked about electrical energy in kilowatt hours. So if I have a 12-volt battery that has a capacity of 1 amp hour, remember if we multiply voltage and current, we get power, correct? And then hour, that's energy. This is equivalent to joule, equivalent to calories, equivalent to kilowatt hour. But the problem is with batteries, a kilowatt is a lot. That's why they choose to make it in amp hours. So 1 amp hour means it would supply 1 ampere of current for an hour, and then it's gonna die. Okay, so a 10 amp hour capacity means it's gonna run for 10 hours at 1 ampere, 5 hours at 2 amperes, 1 hour for 10 amps, and 100 hours for 1 amp. So this brings the equation that the discharge time is the battery rating over the current that is discharging. So it makes sense if you multiply amp hours by amps, divide, amp hours by amps, they cancel out and you end up with time. Okay? So let's do this one. It says a battery is rated on 150 amp hours and is fully charged. How long will the battery last if the load is 3 amps of current? So it's basically 150 amp hour divided by 3 amps is gonna give you 50 hours, because these cancel out. So to recharge secondary batteries, I talked about some people, depends on the type of battery, you can replace the acid. And then another way of discharging the battery, again, depends on the type, is the chemical change can be reversed by supplying current, by sending current back through the cell in the opposite direction from discharging. Okay, so that's the way they recharge batteries. And the time it takes to recharge the cell is based on its capacity in amp hours. And again, the time is the battery capacity over the current that's being fed by the battery charger. So here's an example. A battery rated 150 amp hour has been fully discharged. How long will it take to charge the battery at 5 amperes? So here we write down 150 divided by 5, and this will get you 30 hours. So now, this is an easy topic, batteries in series and in parallel. So you can connect batteries in series, and then you would have to connect them minus plus minus plus minus plus in that typical pattern. Because if you connect them this way, the voltage will add up, and this will be equivalent to 18 volts. However, if you connect them this way, the voltage will not add up, and if you have two 9-volt batteries, you're going to end up with 0 voltage. Okay? So that's important, bear in mind. So in series, voltages add, which is what I just explained, but the current carrying capacity, the current providing ability, okay, is the same as for one single battery. So if these two are 1 amp hour each, my combined capacity is still going to be 1 amp hour, but my combined voltage is going to be 18 volts. This is how it's going to be in real life to connect them in series. So here's 29 volts. The ammeter, the multimeter will measure 18 volts. In parallel, So this is the proper way for wiring. Okay. In parallel, the voltage divided by provided by both batteries is going to be equal to the voltage of one battery. So here, if this is 9 volt, this whole combined set will also provide 9 volts. But the current providing ability is multiplied. Okay, so if every single battery has 1 amp hour, the combined current providing ability will definitely be much higher than 1 amp hour. This is how it's going to be. 9 volts and 9 volts in parallel. Your voltmeter will be reading 4 volts, and then here 2 milliamp hours. Oh, I'm sorry, the current that's being supplied is going to be divided on each one. So if I'm sucking out 4 milliamps, every battery will be providing 2 milliamps. All right, that's it for this lesson today.